Please subscribe to support the channel. In the boundless darkness of the universe, there exists a place so vast and so empty that it challenges everything we think we know about existence. A region where galaxies are scarce, light is rare, and silence reigns across hundreds of millions of light years. It's not a black hole, not a tear in space, but something far stranger. Astronomers call it the Boötes Void, and it is the largest known emptiness in the observable universe, a cosmic abyss that reminds us that most of reality isn't filled with stars and galaxies, but with unimaginable nothingness. When astronomers speak of a void, they're not describing a hole in the universe, not an abyss that swallows matter, nor a rupture in the cosmic fabric. A void is something subtler and far more haunting. It is a vast region of space where galaxies are few and far between. A colossal expanse that seems to stretch endlessly, almost empty of the glittering matter that defines most of the universe we know. If the cosmos were a grand web woven from light and gravity, then voids are the dark spaces between its threads, the cosmic deserts that lie between the clusters of stars. To understand the void, imagine the structure of the universe as something alive and intricate. Over the last few decades, astronomers have come to realize that galaxies are not scattered randomly through space. Instead, they form an immense three-dimensional pattern, often referred to as the cosmic web, an interconnected network of filaments, clusters, and superclusters, made of galaxies, dark matter, and gas. Where the filaments intersect, galaxies crowd together in brilliant clusters. But between those luminous intersections lie vast stretches where matter is scarce. Those are the voids. Calling them empty isn't entirely correct, because no part of the universe is truly devoid of everything. Even in the deepest voids, there are still faint traces of gas, dark matter, and background radiation drifting through the darkness. But compared to the dense regions where galaxies thrive, a void is like an ocean of near nothingness. If you were to travel across one, you could journey for tens or even hundreds of millions of light years before encountering another galaxy. The distances between celestial islands would be so immense that even light, moving at 300,000 kilometers per second, would take ages to cross the silence between them. To the human imagination, it's tempting to equate a void with danger, with black holes, the gravitational monsters that devour everything around them. But a void is nothing like that. A black hole is a place where matter is condensed to an almost infinite density, so dense that even light cannot escape. A void, in contrast, is the opposite, a region where matter barely exists at all. There's no great gravitational pull, no devouring event horizon. The void doesn't consume, it simply is. It's the calm between the storms of creation, a natural byproduct of the universe's own uneven beginnings. When the universe was young, only a few 100,000 years after the Big Bang, it was filled with a nearly uniform sea of gas and energy. Yet, it wasn't perfectly smooth. There were tiny ripples, minute differences in density. Some areas were slightly thicker with matter, others were slightly thinner. Over billions of years, gravity exaggerated those differences. The denser regions pulled in more matter, forming stars, galaxies, and clusters, while the emptier regions grew even emptier as matter drained away from them. The result was the large-scale structure we see today, the cosmic web, crisscrossed with luminous filaments of galaxies and punctuated by immense dark voids. To visualize this, think of a sponge or a honeycomb, a pattern filled with solid walls and hollow chambers. The walls are where galaxies and clusters lie, dense with stars and cosmic dust. The hollow pockets, the spaces between them, are the voids. They are not rare anomalies. In fact, voids make up the majority of the universe's volume. Most of space, statistically speaking, is empty. What we see as the glittering cosmos, the galaxies, nebulae, and star systems, are only the thin glowing boundaries of a much larger, darker expanse. This realization reshaped modern astronomy. For centuries, humans assumed the universe was mostly filled with stars, that space was just a vast canvas dotted with light.
But as our telescopes became more powerful and our surveys more precise, we discovered that light is the exception, not the rule. Emptiness dominates everything. Roughly 80% of the volume of the observable universe lies within these voids. The galaxies, magnificent as they are, float like luminous specks in a cosmic sea of absence. From an observational standpoint, identifying a void isn't as straightforward as spotting a star or a galaxy. Astronomers can't see a void directly. There's nothing to shine, nothing to emit light. Instead, they detect them by charting where galaxies aren't. Massive surveys like the Sloan Digital Sky Survey map the positions of millions of galaxies across billions of light years. And when those maps are plotted in 3 dimensions, patterns begin to emerge. Clusters and filaments stand out like glowing webs, and in between, vast dark spheres appear, the voids. These voids are not mistakes or gaps in data. They are real features of the universe, as much a part of its structure as the galaxies themselves. A void's boundaries aren't sharp or fixed. They gradually blend into the filaments that surround them, much like the edges of clouds merging with the sky. Inside, the density of matter can be hundreds of times lower than average. The few galaxies that do exist within them often appear as faint, isolated wanderers, cosmic nomads far from any neighboring cluster. These galaxies evolve differently from those in denser regions. Without nearby gravitational companions to tug or merge with, they live quieter, slower lives. Some scientists even believe that studying galaxies within voids could reveal secrets about how environment shapes cosmic evolution, offering a glimpse of what the early universe's first lonely galaxies might have looked like. But despite their vast emptiness, voids are not mere cosmic afterthoughts. They play a critical role in balancing the structure of the universe. Their expansion pushes on the filaments, helping shape the large-scale geometry of space itself. In a sense, the voids and the filaments dance together, emptiness defining structure and structure defining emptiness. One cannot exist without the other.
Understanding this balance helps explain why the discovery of the Boötes Void was so astonishing. Astronomers expected to find voids, small ones, tens of millions of light years across, scattered between galaxy clusters. But the Boötes Void was an entirely different creature. It was not a modest pocket of low density. It was an expanse, hundreds of millions of light years wide, so empty that it defied the models of the time. It showed that the universe's architecture was even more extreme than scientists had dared to imagine. And yet, to call it nothing would still be inaccurate. The Boötes Void, like every other void, hums faintly with the invisible substance that threads through all space, dark matter and dark energy. These unseen components, which make up the majority of the universe's total content, permeate even the emptiest regions. They shape how galaxies move, how light bends, how the universe expands. So a void isn't truly void. It's more like a whisper of existence, the faint outline of the cosmos where light and matter have thinned but not vanished completely. The beauty of understanding what a void really is lies in how it changes our perception of everything else. When we look at the night sky, we tend to focus on what shines, the stars, the galaxies, the glowing nebulae. But astronomy teaches us that the universe's story is just as much about the spaces between those lights. The voids define the structure of the cosmos, just like bones define the shape of a body. Without them, there would be no contrast, no pattern, no cosmic web. The Boötes Void, and its kin, remind us that absence itself is a form of creation, that even nothingness has architecture. And so when we talk about the Boötes Void as the biggest hole in the universe, we're not describing a wound or a tear. We're describing one of the universe's quietest symphonies, a vast, silent region sculpted by time and gravity, a place where the density of matter dips to nearly nothing. It's not destruction, it's balance. The voids are the universe's resting places between the bursts of creation. As we move forward, it becomes important to see how this concept of cosmic emptiness fits within the grander structure of everything that exists. Because to truly appreciate the Boötes Void,
To grasp why it stands as one of the largest and most mysterious features of the observable cosmos, we need to understand the scale on which the universe built itself. Galaxies form clusters, clusters form filaments, and between those filaments stretch the immense silent gulfs like Boötes itself. Only by setting the scale of the cosmos can we begin to comprehend what it means for something to be that big, that empty, and that real. To understand where the Boötes Void belongs in the grand architecture of the cosmos, we must first step back, far back, and look at the universe not as a scattering of stars or a collection of galaxies, but as a vast interconnected system. When we zoom out beyond the familiar scale of planets, solar systems, and galaxies, a hidden pattern begins to emerge, one that defines the true shape of everything. This pattern is what cosmologists call the large-scale structure of the universe, and it is one of the most breathtaking discoveries of modern astronomy. At its most fundamental level, the universe is not a random sprawl of galaxies drifting through endless space. Instead, it is organized into an immense cosmic web, an intricate network made of luminous filaments and vast empty regions, woven together by the invisible threads of gravity and dark matter. The galaxies that we see through our telescopes are not scattered haphazardly. They trace these threads, forming clusters and filaments that stretch for hundreds of millions of light years. The result is a structure that resembles a three-dimensional map of foam or lace, a universe made not of uniformity, but of texture.
This texture is hierarchical. On smaller scales, galaxies gather together to form groups, like our local group, which includes the Milky Way, the Andromeda Galaxy, and about 50 smaller companions. These groups, bound by gravity, merge into larger clusters, which may contain hundreds or even thousands of galaxies. Some of these clusters are so massive that their collective gravity bends light from objects far behind them, a phenomenon known as gravitational lensing. Clusters then connect to one another through vast bridges of matter, forming enormous filaments, the glowing strands of the cosmic web. If we could see the entire observable universe from a godlike vantage point, it would not look like a field of evenly sprinkled stars. It would look more like a colossal network of veins and nodes, glowing with the light of billions of galaxies. The filaments intersect at dense knots where clusters lie, and between those knots are the dark cavernous expanses, the voids. These voids are not small gaps, but enormous cosmic basins stretching for tens or even hundreds of millions of light years across. It's within one of these immense regions of near nothingness that the Boötes Void resides, one of the grandest of all. In a sense, the cosmic web is a skeleton of the universe. It gives structure to the vast emptiness, mapping where matter has gathered over billions of years since the Big Bang. Yet the web is not made only of galaxies and gas. Much of its structure is composed of dark matter, the invisible substance that outweighs ordinary matter by a factor of 5. Though dark matter cannot be seen directly, its gravitational influence sculpts the universe on every scale, drawing galaxies into clusters and leaving behind the dark pockets that become the voids. Astronomers have pieced together this enormous structure using decades of observation and mapping. Surveys like the CFA Redshift Survey and later the Sloan Digital Sky Survey charted the positions and redshifts of hundreds of thousands of galaxies, revealing how they form filaments and sheets surrounding vast empty spaces. When these data are visualized in 3 dimensions, the universe appears as a luminous sponge, glowing tendrils enclosing hollow bubbles. It's a stunning realization. The cosmos is not solid, not dense, but mostly empty. The light we see, every star, every galaxy, traces only the thinnest filigree of a far greater design. The scale of this design defies intuition. Our own Milky Way galaxy spans about 100,000 light years, and yet the cosmic filaments can stretch for hundreds of millions of light years. Between them, the voids expand like dark oceans, some as large as 300 million light years across,
as in the case of the Boötes Void. These distances are so vast that numbers alone fail to capture their enormity. Light itself, traveling at nearly 186,000 miles per second, would take hundreds of millions of years to traverse one of these voids from side to side. It's as though the universe is a delicate web suspended across an infinite abyss, its bright filaments separated by gulfs of immeasurable silence. What's remarkable about the cosmic web is how closely it matches the predictions of cosmology. Computer simulations of the universe's formation, such as the Millennium simulation, show that when matter is allowed to evolve under the influence of gravity and dark energy, it naturally forms this web-like pattern. Small fluctuations in density in the early universe grow over time. Denser regions attract more matter and form filaments, while emptier regions expand into voids. This process is still unfolding today, as the universe continues to expand and the contrast between structure and emptiness becomes ever sharper. In this context, the Boötes Void is not an anomaly, but an extreme example of the universe's natural design. It's a vast bubble in the foam, one of the largest known cavities within the web. Imagine the universe as a cosmic honeycomb. The Boötes Void is one of its biggest cells. Its sheer size and emptiness make it an exceptional case, a kind of cosmic supervoid that dwarfs most of the others we've observed. Where the typical void might span 50 to 100 million light years, Boötes stretches roughly 330 million. It's as if an entire section of the cosmic web simply failed to form there. To grasp just how rare that is, consider that if galaxies were sprinkled evenly across the universe, we would expect to find thousands of them in any region that large. Yet inside the Boötes Void, astronomers have found only about 60. It's a structure that pushes the limits of what our cosmological models predict, so large and so empty that it challenges our understanding of how the universe evolved.
But before the Boötes Void was discovered, the concept of such an immense void wasn't even imagined. When astronomers first began mapping the cosmos in the late 20th century, they expected galaxies to be roughly evenly distributed, with perhaps small patches of lower density. The revelation that the universe was structured into filaments and voids came as a shock. It was as though humanity had pulled back the curtain on the architecture of creation itself and found it built on both presence and absence, on light and darkness intertwined. Seen in this light, the Boötes Void isn't just a curiosity, it's a critical piece of the cosmic puzzle. It shows that the universe is not homogeneous on the largest scales. Instead, it's a tapestry of density and emptiness, a pattern that tells the story of gravity, time, and expansion. The Boötes Void marks the outer limit of that pattern, the place where the cosmic web grows thin and silence takes over. It's within this grand context that the Boötes Void truly reveals its significance. It's not just a hole in the sky. It's one of the deepest valleys in the cosmic landscape, a vast lowland in the topography of existence. It reminds us that the universe's beauty doesn't come only from what is there, but also from what is missing. And now that we've placed the Boötes Void within the grand cosmic map, a lonely abyss suspended between the filaments of galaxies, we can turn our gaze directly toward it. We can explore where it lies, how it was found, and what makes it so extraordinary among the great voids of space. When we turn our eyes toward the constellation of Boötes, a region of the northern sky marked by the bright orange star Arcturus, we are gazing not merely at a familiar pattern of starlight, but toward one of the most astonishing cosmic features ever discovered, the Boötes Void. Hidden in that direction, far beyond the reach of ordinary vision, lies a realm so vast and so empty that it seems to defy logic. The Boötes Void isn't just another space between galaxies. It is one of the largest known voids in the observable universe, a cosmic cavity stretching across hundreds of millions of light years, a silent monument to the power of cosmic evolution and the mystery of nothingness. At first glance, the name Boötes Void might sound poetic, but its origin is purely descriptive. Astronomers identify regions of the sky based on their position relative to known constellations,
and this colossal void happens to lie in the direction of Boötes, the herdsman. If you could somehow travel through that region, you would not encounter a single star for unfathomable distances. For all practical purposes, you would be drifting through an ocean of near total darkness, a space where galaxies are so few and far between that the very concept of proximity loses meaning. The Boötes Void occupies a place roughly 700 million light-years from Earth, and its size is staggering, about 330 million light-years across. To put that in perspective, if our entire Milky Way galaxy, with its 100 billion stars, were a single point of light, you could fit several million Milky Ways side by side across the diameter of this void. This is not merely a gap between galaxy clusters. It's a region of space that seems to have been largely forgotten by creation itself. Compared to the crowded filaments and superclusters that dominate other regions of the cosmos, Boötes is a cosmic desert.
For astronomers, what makes the Boötes Void so extraordinary is not simply its emptiness, but its scale. Typical voids, the vast, underdense regions that fill much of the universe, tend to measure between 30 and 100 million light-years across. Even these are immense. But the Boötes Void surpasses them by a factor of 3 or more. It's not just large, it's exceptionally large. So much so that it pushes the boundaries of what cosmological models predict. Its existence demands explanation. How could such a vast, underpopulated region form in a universe governed by the uniform laws of gravity and expansion? Yet despite its enormity, the Boötes Void is not a complete nothingness. Deep within its cavernous interior lie about 60 galaxies, faint and scattered like islands in an endless night. These galaxies are separated by distances so vast that they can never influence each other gravitationally in any meaningful way. Each one is a lonely outpost shining into the void with no neighboring systems close enough to tug, merge, or collide, events that are common in denser regions of the universe. In that sense, the Boötes Void isn't a true vacuum, but it's as close as nature seems willing to allow. What's even more remarkable is that this enormous void occupies a significant fraction of the cosmic web's volume in its region of space. If you could view the Boötes Void within the three-dimensional structure of the universe, surrounded by filaments of galaxies and clusters, it would appear as a vast bubble, almost perfectly spherical, nestled among the threads of cosmic light. Its sheer size and smoothness make it stand out even among the largest voids ever observed. Astronomers often describe it as a supervoid, a term reserved for only the most extreme examples of these colossal empty regions. When it was first identified, scientists were astonished not just by how big it was, but by what it implied. The Boötes Void occupies roughly 0.27% of the observable universe, a staggering proportion for a single feature. That might sound small, but on the cosmic scale, it's monumental. Its discovery forced researchers to reconsider their understanding of how galaxies and large-scale structures formed in the early universe. If the universe began with small density fluctuations, tiny irregularities in the otherwise uniform sea of matter after the Big Bang, then over billions of years, gravity should have caused those differences to grow into clusters and filaments, leaving behind the voids. But a void as large and as smooth as Boötes seemed to require either an exceptional amount of time or some unusual set of initial conditions. The location of the Boötes Void also adds to its intrigue. When astronomers map the distribution of galaxies in that part of the sky, the void reveals itself not as an absence of light, but as a colossal gap in the pattern. Surrounding it are regions dense with galaxies, the Hercules supercluster, the Coma cluster, and other luminous concentrations that form the walls of the cosmic web. It's as if the Boötes Void were carved out of the universe's structure, a hollow sphere enclosed by ribbons of light. From a structural perspective, the void acts as a counterweight to these dense regions, a balancing emptiness that gives the cosmic web its characteristic texture. The Boötes Void has earned many poetic nicknames since its discovery: the Great Nothing, the Cosmic Desert, the Universe's Empty Heart. Each name captures a different shade of its mystery. For some scientists, It represents a natural outcome of cosmic evolution, a vast region that simply happened to start off with slightly less matter than its surroundings. For others, it remains a puzzle, an extreme outlier that tests the limits of our cosmological models. Either way, it stands as one of the most awe-inspiring examples of how structure and emptiness coexist on the grandest scales imaginable. If one were to drift at the center of the Boötes Void, the view would be unlike anything possible elsewhere in the universe. The night sky would be almost blank, where the Milky Way glitters with hundreds of billions of stars, and the deeper universe reveals galaxies by the millions. Inside the Boötes Void, the heavens would appear nearly empty. Only a few distant smudges of light would mark the locations of far-off galaxies, faint and lonely in the distance. The silence there would be absolute, not because there's no sound, but because there's nothing nearby to make any. In that sense, the Boötes Void is not merely a place, it is the embodiment of cosmic isolation. What makes the Boötes Void so fascinating is that it bridges two extremes of reality. On one hand, it's a testament to the power of the physical laws that shape the cosmos: gravity, expansion, and time sculpting matter into patterns that span billions of light years. On the other hand, it's a philosophical symbol, a reminder that the universe's beauty lies not only in what it creates, but also in what it leaves behind. In the grand dance of galaxies and stars, the voids are the pauses, the silent intervals that make the symphony whole. So, as we focus our gaze upon that quiet corner of the sky, somewhere in the direction of Boötes, we are not merely looking at a patch of blackness, we are staring into one of the largest single structures ever discovered. A space so immense and so still that it may as well be the universe taking a breath. And with its existence now brought into focus, the next question naturally follows. How big is it really? How can we possibly comprehend a void so enormous that our own galaxy would be a mere speck within it? To appreciate the Boötes Void in full, we must now attempt to measure the unmeasurable, to put its immensity into perspective, and to understand just how vast nothing can truly be. The sheer scale of the Boötes Void is almost impossible to grasp, even for scientists accustomed to thinking in terms of billions of light years. At roughly 330 million light years across, this void is a staggering expanse of emptiness, a cosmic chasm so vast that ordinary comparisons almost fail. To begin to comprehend its size, it helps to start with something familiar: our own galaxy, the Milky Way. The Milky Way, a sprawling spiral of roughly 100,000 light-years in diameter, is considered enormous on human scales, a city of hundreds of billions of stars. Yet, when placed inside the Boötes Void, it would seem infinitesimal, like a single grain of sand in a vast desert stretching endlessly in every direction. Visualizing this is challenging. If you try to line up the Milky Way across the void, you could fit more than 3,000 Milky Ways side by side, with space left over. Each of our familiar galaxies, with their clusters of stars, planets, and nebulae, would become almost inconsequential in comparison to the vast emptiness around them. The void's enormity is not simply a matter of distance. It is a space so empty and so silent that any sense of scale that humans naturally use begins to crumble under the weight of its magnitude. Consider the distances between galaxies within more typical regions of the universe. In our cosmic neighborhood, the nearest large galaxy, Andromeda, is about 2.5 million light-years away. Even that seems inconceivably far. Yet the Boötes Void is more than 100 times larger than that separation, stretching across a span that dwarfs even entire superclusters. It is, in effect, a region where galaxies are scattered at such great distances that they are almost invisible to each other in a gravitational sense. Interaction between galaxies, collisions, mergers, tidal effects almost entirely ceases. It is as though the void is a sanctuary of isolation, a place where the normal cosmic dance of matter slows to a near standstill. Another way to understand this immense size is to think about light itself. Light travels at approximately 186,000 miles per second, and even at that unimaginable speed, it would take 330 million years to cross the void from one edge to the other. A photon of light leaving one galaxy on one side of the Boötes Void would reach the opposite boundary long after civilizations, stars, and even entire galaxies had evolved elsewhere. In human terms, we cannot hope to experience the full breadth of the void. It exists on a scale so vast that it transcends intuitive comprehension, demanding that we expand our minds to encompass it. Even more striking is the comparison with the Milky Way's total content of stars. If the Boötes Void were filled with Milky Ways at the density of our local group, there would be millions upon millions of galaxies inside it. Yet in reality, there are only about 60 galaxies scattered sparsely throughout this enormous region. That contrast, the gulf between what we might expect and what actually exists, is what makes the void so extraordinary. It is not merely a low-density region, it is an almost unimaginable absence of matter on a colossal scale. To picture it another way, imagine the Milky Way as a single city. The average void could then be thought of as a continent, and the Boötes Void itself as a planet-spanning desert. While most of the universe is occupied with bustling clusters of galaxies, interconnected filaments, and luminous superclusters, the Boötes Void is a silent, almost alien landscape. Even the few galaxies it contains appear as lonely outposts in a vast sea of nothingness, separated by distances that render them effectively isolated from one another. The emptiness is so extreme that if we were to place Earth at the center of the Boötes Void, the nearest galaxy visible to us might be tens of millions of light years away. The sky would not glitter with stars and nebulae. Instead, it would be dominated by darkness, punctuated only by the faint glow of a few remote galaxies. The experience would be unlike anything encountered elsewhere in the universe, a profound isolation in a space that dwarfs even the largest of our cosmic landmarks. This immense size also highlights why the Boötes Void captured such fascination when it was first discovered. Scientists expected voids to exist, certainly, but none had predicted one of this magnitude. Typical voids might stretch across 30 to 100 million light-years, significant, yet comprehensible on the cosmic scale. Boötes, however, stretches 330 million light-years, 3 to 10 times larger than these more common voids. It is a truly extreme example of a cosmic supervoid, testing the limits of what our models of galaxy formation and evolution can explain. It's this combination of vast emptiness and sheer scale that makes the Boötes Void more than just a curiosity. Its size challenges our understanding of the early universe, of how gravity and matter interacted over billions of years, and of the ways in which galaxies and clusters coalesced. By studying it, scientists can explore not just the nature of voids, but the broader principles of cosmic architecture, and even the underlying roles of dark matter and dark energy in shaping the universe. Ultimately, emphasizing the immense size of the Boötes Void is a way to confront the mind with the vastness of the cosmos itself. It forces us to realize that, on the largest scales, the universe is dominated not by presence but by absence. That emptiness is not an occasional feature, but a fundamental part of the cosmic design. It reminds us that space, even in its quietest, most desolate forms, is capable of a scale beyond human comprehension, stretching across hundreds of millions of light years, containing within it the ultimate measure of cosmic solitude. Having grasped the magnitude of this void, the natural next step is to understand how it was discovered, how astronomers, armed with maps of galaxies and the faint light of distant stars, first realized that such a colossal and empty region even existed, and how its discovery reshaped our view of the universe. The discovery of the Boötes Void is as fascinating as the void itself, and it reads almost like a detective story played out on a cosmic scale. It was in 1981 that astronomer Robert Kirshner, along with his colleagues, stumbled upon what would soon be recognized as one of the most remarkable features of the observable universe.
At the time, astronomers were engaged in mapping the large-scale distribution of galaxies, attempting to chart the universe in 3 dimensions by measuring the redshifts of their light, the slight shifts in their light caused by the expansion of the universe. Their goal was simple in concept: to understand how galaxies were arranged across vast stretches of space. Yet, as their maps unfolded, something astonishing emerged. While examining the galaxies in the direction of the Boötes constellation, Kirshner's team noticed a peculiar pattern, or rather, the lack of one. In an area where galaxies should have been relatively abundant, there was an enormous region almost entirely devoid of them. For hundreds of millions of light-years in every direction, the team found only a handful of galaxies, far fewer than expected. Initially, some speculated that this might be a fluke, a result of incomplete data or observational error. After all, the technology of the time was limited, and mapping the universe on such a large scale was an enormous challenge. But as the team collected more data and cross-checked their measurements, it became increasingly clear that this was no accident. The emptiness was real. Kirshner and his colleagues realized they had stumbled upon a cosmic void of unprecedented size, a region so large and so sparsely populated that it defied all prior expectations. The sheer scale of the Boötes Void, roughly 330 million light-years across, was what made it extraordinary. While astronomers had theorized the existence of voids, none had predicted one of such magnitude, containing so few galaxies across such a vast distance.
The discovery process relied heavily on redshift surveys, a technique that measures the displacement of spectral lines in the light emitted by galaxies. This displacement occurs because the universe is expanding. Galaxies moving away from us stretch the wavelength of their light, shifting it toward the red end of the spectrum. By measuring the degree of redshift, astronomers could determine not just how far away a galaxy was, but also its position in 3-dimensional space. When Kirshner's team plotted thousands of galaxies this way, the void appeared as a massive spherical gap, a true cosmic anomaly in the otherwise web-like distribution of matter. What was particularly remarkable was that the Boötes Void was not just a slightly underpopulated area. The density of galaxies inside it was astonishingly low, roughly 10 times lower than the average density in the universe. While the surrounding universe was filled with clusters, filaments, and superclusters of galaxies, the Boötes Void seemed almost eerily empty. Only about 60 galaxies had been identified inside the entire expanse of the void, making it a lonely outpost in the cosmic web. For astronomers, this was a profound surprise, a phenomenon that required a rethinking of galaxy formation and the evolution of large-scale structures. The context of the discovery also highlights the ingenuity and patience required in observational astronomy. Before the void could be identified, researchers had to painstakingly catalog countless galaxies, measure their redshifts, and analyze their spatial distribution. Each galaxy represented a faint glimmer, often millions or even billions of light-years away, and the void's presence could only be inferred from the absence of these glimmers over a vast volume of space. It was, in essence, a discovery made by noticing where the universe was silent rather than where it shone. Kirshner's work opened a new chapter in cosmology. Prior to the discovery of such supervoids, astronomers often envisioned the universe as a relatively uniform expanse punctuated by clusters and isolated galaxies. The Boötes Void, however, shattered that notion. It revealed that the universe is far from homogeneous on these enormous scales. Instead, it is dominated by structure and emptiness, intricately woven together in a cosmic web. The void's size, shape, and extreme paucity of galaxies made it a striking counterpoint to the luminous region surrounding it, emphasizing the dynamic interplay between matter and emptiness that defines the cosmos. The discovery of the Boötes Void also sparked a wave of speculation and debate. Some wondered if it could be a relic of an unusual primordial fluctuation in the density of matter, while others considered more exotic explanations, such as the influence of dark energy or even the hypothetical effects of topological defects in space-time. While subsequent research has largely confirmed that the void is a natural consequence of gravitational evolution, the initial discovery demonstrated the power of observational astronomy to reveal the unexpected. In essence, Kirshner and his team taught us an important lesson. The universe is not only defined by what exists, but also by what is absent. By mapping the cosmos, they uncovered a region where the normal processes of galaxy formation had left a profound void, an enormous bubble in the cosmic web where almost nothing had formed. The Boötes Void is a monument to the universe's extremes, a silent, sprawling space that forces astronomers to confront the limits of scale, density, and the imagination itself. The story of its discovery is a testament to human curiosity and ingenuity, a reminder that the cosmos often hides its most remarkable secrets not in what we see, but in the vast, silent expanses where we see nothing at all. With its discovery, the Boötes Void immediately became a key object of study, not merely because of its emptiness, but because it challenged scientists to explain how such an immense emptiness could arise from the same physical laws that created the galaxies and clusters elsewhere in the universe. Having understood how the Boötes Void was discovered and appreciating the meticulous observation, measurement, and analysis that revealed it, we can now turn our attention to what lies inside this enormous emptiness. Though it is overwhelmingly barren, the void is not entirely devoid of matter, and the few galaxies that do exist within it offer clues to the history and nature of this vast cosmic desert. The Boötes Void, despite its staggering size and reputation as the Great Nothing, is not completely empty. Within this vast expanse, roughly 330 million light-years across, astronomers have identified about 60 galaxies. On the surface, that may sound like a reasonable number, but when compared to the sheer volume of space the void occupies, it is almost inconceivably sparse. These 60 galaxies are scattered across a region so immense that in terms of density, the Boötes Void is practically a cosmic desert. Where the universe on average contains dozens of galaxies in the volume of a typical cluster, the void's interior has only a handful, making it one of the most extreme low-density regions ever observed. The galaxies that do exist within the void are small, faint, and isolated. Unlike galaxies embedded in clusters or filaments which interact, merge, and influence one another, the void's galaxies lead solitary lives. They are gravitationally isolated, often separated from their nearest neighbor by tens of millions of light-years. This separation has profound implications for their evolution. Without the interactions and mergers that shape the morphology and activity of galaxies in denser regions, the void's galaxies tend to evolve more slowly, their star formation rates often lower, and their structures simpler. These galaxies can be seen as relics or laboratories, offering astronomers a rare glimpse into how galaxies might behave in isolation, unaffected by the crowded environment that dominates the rest of the cosmos. One of the most striking aspects of the Boötes Void is the contrast between the number of galaxies expected and the number actually present. If the void were filled with galaxies at the average cosmic density, astronomers would expect to find thousands or even tens of thousands of galaxies in that same volume. Instead, the reality is drastically different. A region that could contain millions of galaxies, if typical cosmic density prevailed, instead holds only a handful. This extreme scarcity makes the void's emptiness all the more striking, emphasizing how extraordinary it is in both size and isolation. The galaxies inside the void are often dim and diffuse, making them difficult to observe, even with powerful telescopes. Many are dwarf galaxies, small and faint compared to giants like the Milky Way or Andromeda. Their low luminosity and isolated locations mean they have received comparatively little attention in the past, but modern surveys have begun to catalog and study them in detail.
These galaxies provide critical insight into the processes that govern star formation and galactic evolution in low-density environments, helping astronomers understand how isolation affects the life cycle of galaxies.
It's important to note that although the void contains only a small number of galaxies, it is not an absolute vacuum. Even within its sparsely populated interior, the Boötes Void still contains traces of intergalactic gas, dark matter, and cosmic background radiation. These components are invisible to optical telescopes, but exert influence over cosmic evolution. Dark matter, in particular, provides the gravitational scaffolding that shapes the structure of the universe. Even in a region with almost no luminous matter, the underlying presence of dark matter subtly shapes the motion and behavior of the few galaxies that exist within the void. The sparsity of the Boötes Void makes it a unique natural laboratory. Studying the few galaxies it contains allows scientists to test theories of galaxy formation and evolution under extreme conditions. In denser regions, galaxies frequently interact, merge, and experience tidal forces that significantly alter their development. In contrast, the void's galaxies evolve largely undisturbed, providing a clearer window into the intrinsic processes that govern star formation, gas retention, and the chemical enrichment of galaxies over cosmic time. The contrast between the interior of the void and the bustling filaments and clusters that surround it is staggering. While dense regions of the universe teem with galaxies forming the bright threads of the cosmic web, the Boötes Void is almost silent. Its galaxies are few and far between, their faint light a stark reminder of the scale of emptiness that exists even within a universe so full of stars elsewhere. In a sense, the Boötes Void emphasizes not only the enormity of space, but also the rarity of matter on the largest scales. It is a cosmic lesson in absence, showing that while the universe is abundant with stars and galaxies, it is even more dominated by empty space. Even from a distance, when astronomers map the void, the galaxies inside it appear as isolated dots against the blackness, scattered like lonely islands in a vast, dark ocean. Each galaxy is separated by tens of millions of light-years, a distance that prevents any meaningful gravitational interaction with its neighbors. The few galaxies that exist there can be considered pioneers of the void, survivors of a cosmic desert where the universe itself has largely failed to deposit matter. Studying these galaxies also sheds light on the formation of voids themselves. The presence of a few galaxies suggests that the Boötes Void did not form instantaneously or through some violent event, but rather gradually, as regions of slightly lower initial density expanded over billions of years. Matter slowly drained away from the interior toward the surrounding filaments and clusters, leaving behind the sparse collection of galaxies that we see today. In this sense, the void and its few galaxies are evidence of the same natural processes that shaped the entire cosmic web: gravity, expansion, and the uneven distribution of matter in the early universe. The Boötes Void reminds us that emptiness is not a simple absence of existence. Even in one of the most barren regions of space, there are galaxies, intergalactic gas, and the invisible scaffolding of dark matter. The void is not nothing. It is a place where the normal density of the universe has been dramatically reduced, creating a cosmic laboratory where isolation and emptiness dominate. Ultimately, what lies inside the Boötes Void, these roughly 60 scattered galaxies, reinforce the sense of scale, solitude, and mystery that defines this remarkable structure. They serve as tiny beacons within an otherwise empty expanse, highlighting both the void's enormous size and its profound lack of matter. These galaxies are survivors in a region of space that seems almost designed to challenge our intuition, a reminder that the universe is defined as much by the spaces between galaxies as by the galaxies themselves. By examining what lies inside the Boötes Void, we prepare to understand how such voids form, why the universe contains regions of such extreme emptiness, and what these cosmic deserts reveal about the evolution of the cosmos on the largest scales. The formation of cosmic voids, including the Boötes Void, is deeply tied to the very beginnings of the universe itself. To understand how such enormous emptiness comes to exist, we must turn back the cosmic clock to the universe's infancy, mere hundreds of thousands of years after the Big Bang. At that time, the universe was filled with a nearly uniform soup of hot gas, dark matter, and radiation. Yet this soup was not perfectly smooth. It contained tiny irregularities in density, minuscule fluctuations where some regions were slightly denser than others and some slightly emptier. These small differences, though nearly imperceptible, would set the stage for the vast cosmic web we see today. Gravity is the key actor in this cosmic drama. In regions that were denser than average, gravity began to pull matter inward, drawing gas, dust, and dark matter toward these seeds of structure. Over time, this led to the formation of stars, galaxies, and clusters, the luminous filaments and nodes that trace the cosmic web. Meanwhile, regions with slightly less matter experienced the opposite effect. With fewer gravitational forces acting to retain material, these areas gradually became emptier as surrounding matter flowed outward toward the denser regions. This process, occurring over billions of years, naturally amplified the initial tiny differences, leaving behind the vast underdense regions we now call voids. Voids like Boötes are the extreme outcome of this process. While most voids may span tens of millions of light years, the Boötes Void represents an extraordinary amplification of these early fluctuations. Its enormous size suggests that the initial region was slightly less dense than its surroundings, and that over cosmic time, the gravitational migration of matter away from this area continued unabated, leaving behind an almost completely empty expanse. In essence, the Boötes Void is a magnified imprint of the universe's primordial structure, a relic of the density variations present at the dawn of time. The process of void formation is intimately tied to the behavior of dark matter, the invisible substance that makes up roughly 85% of the universe's matter. Dark matter interacts gravitationally, but not electromagnetically, which means it doesn't emit or absorb light. Yet its presence is crucial for shaping the universe. Dark matter formed the scaffolding on which ordinary matter could gather, pulling gas and dust into the growing filaments and clusters. In regions where dark matter density was lower, gravitational attraction was weaker, leading to the expansion of underdense regions and the development of voids. Without dark matter, the cosmic web, with its filaments and voids, would likely look very different, and structures like the Boötes Void might never exist. Voids continue to evolve even today. As the universe expands, these underdense regions grow larger, not because matter disappears, but because the surrounding higher density regions pull material outward. In this sense, voids are dynamic features of the cosmic web, actively shaped by the gravitational interplay of matter and the expansion of space. The emptiness we see now is the cumulative result of billions of years of cosmic evolution, stretching the initial slight irregularities into vast, nearly empty cavities like the Boötes Void. Interestingly, voids also influence their surroundings. The expansion of a void exerts pressure on adjacent filaments, subtly shaping the distribution of galaxies and clusters around it. This feedback between emptiness and structure is a fundamental aspect of the universe's large-scale architecture. The Boötes Void, with its enormous volume and relative isolation, exemplifies this principle. It is not merely a passive gap, but an active component of the cosmic web, interacting gravitationally with the dense structures that surround it.
Scientists can't simulate the formation of voids using sophisticated cosmological models. Computer simulations such as the Millennium Simulation or Illustris begin with small density fluctuations in a virtual early universe and allow matter to evolve under the influence of gravity, dark energy, and cosmic expansion. Remarkably, these simulations naturally produce networks of filaments, clusters, and voids that closely resemble what we observe in the real universe. The Boötes Void, while extreme, fits into this framework,
demonstrating that even the largest empty regions are consistent with the natural evolution of the universe's structure from its initial conditions. Voids also provide insight into the behavior of dark energy, the mysterious force driving the accelerated expansion of the universe. In low-density regions like Boötes, the effects of dark energy are more pronounced relative to gravity. As a result, voids expand faster than the denser regions around them, contributing to the overall acceleration of cosmic expansion. By studying voids, astronomers gain a unique laboratory to understand the interplay between matter, gravity, and dark energy, offering clues about the underlying forces shaping the cosmos. In summary, voids formed through a natural process of gravitational amplification of primordial density fluctuations. Slightly underdense regions in the early universe gradually lost matter to their surroundings, growing emptier over billions of years. In the case of the Boötes Void, this process produced an extraordinarily vast region, a nearly empty bubble suspended in the cosmic web. Its existence underscores the universe's remarkable capacity for extremes, where both matter and emptiness are sculpted by the same fundamental forces. By understanding how voids form, we gain context for why the Boötes Void is so extraordinary, yet also why it is a natural consequence of the universe's evolution. The next step is to place it among other voids, comparing it with the rest of the cosmic web and understanding how it stands out as one of the most remarkable empty regions ever discovered. Voids are not rare curiosities scattered randomly across the universe. They are a fundamental feature of the cosmic web. When astronomers map the positions of galaxies on the largest scales, voids appear as a recurring pattern, vast regions of low density nestled between the filaments and clusters of galaxies. These empty regions, though varying in size and shape, are ubiquitous, forming an essential part of the universe's architecture. They define the spaces in which galaxies do not exist, highlighting the contrast between luminous matter and the vast emptiness that dominates cosmic volume. Most voids are relatively modest in size, stretching across tens of millions of light-years. For example, the Eridanus Void, located in the constellation Eridanus, is one of the largest previously known voids, spanning roughly 200 million light-years. That is a tremendous distance by any human standard. Yet, when compared to the Boötes Void, it is noticeably smaller. The Boötes Void, at approximately 330 million light-years across, represents an extreme in both size and isolation. It is not just another empty space. It is a supervoid, a term used to describe the very largest voids that push the boundaries of what is observed and predicted in the cosmic web. The Boötes Void stands out because of its smooth, spherical shape and its remarkable uniformity. Many voids have irregular boundaries, or are elongated, shaped by the filaments and clusters that surround them. Boötes, by contrast, appears almost like a perfectly sculpted bubble in the fabric of space, with relatively few galaxies scattered throughout its interior. This combination of size and sparsity makes it one of the most extreme examples of cosmic emptiness. While other voids may reach impressive scales, none are so nearly devoid of galaxies relative to their volume, making Boötes uniquely striking in the catalog of known cosmic voids. Even among voids of comparable size, Boötes is exceptional. For instance, the Sloan Great Wall region contains both dense superclusters and adjacent voids of extraordinary volume. But the Boötes Void is distinctive because it is both extremely large and exceptionally empty, a combination rarely observed elsewhere. Its relative isolation amplifies its significance. Unlike voids embedded within more complex networks of structures, Boötes is a true cosmic gulf, a nearly pristine region of emptiness that stretches across the cosmic web without interruption. Astronomers also note that voids differ in their galaxy content and morphology. Smaller voids may contain dozens of galaxies, often irregular or dwarf systems, while larger voids like Boötes contain only a handful of widely separated galaxies. These differences allow scientists to classify voids based on size, density, and evolutionary history. Boötes, due to its enormous volume and extremely low density, occupies the upper extreme in all three categories, making it not just an empty region, but a benchmark against which other voids are measured. The comparative study of voids also sheds light on cosmic evolution.
By examining voids of different sizes and densities, astronomers can trace how small differences in the early universe's matter distribution led to the large-scale features we see today. Smaller voids reflect typical density fluctuations, forming as matter coalesced into surrounding filaments. Boötes, on the other hand, likely originated from a particularly underdense region in the early universe, magnified over billions of years by gravitational dynamics and cosmic expansion. Its extremity provides a unique test for cosmological models, showing how natural processes can produce even the largest and most isolated empty regions. In addition to its size and sparsity, Boötes is remarkable because it is one of the most studied voids. Its discovery sparked a wave of research into supervoids, prompting astronomers to survey other large regions of the sky for similar features. While multiple voids of comparable size have since been cataloged, Boötes remains the most famous and visually dramatic, serving as a reference point in the study of cosmic emptiness. By comparing Boötes with other voids like Eridanus, the local void near our own Milky Way, or other underdense regions identified by the Sloan Digital Sky Survey, researchers gain perspective on both the diversity and the regularity of these structures. Despite being unusual, Boötes still fits into the broader statistical pattern of voids. Simulations of the universe consistently produce voids of varying sizes, demonstrating that emptiness is a natural consequence of gravitational evolution and the growth of cosmic structures. What makes Boötes so striking is not that it shouldn't exist, but that it represents the extreme upper end of this natural spectrum, a region where the forces that govern the distribution of matter conspired to produce a supervoid of unparalleled scale and relative isolation. The comparison to other voids also highlights a crucial point. The universe is dominated by emptiness. While galaxies, clusters, and filaments form the luminous web we can see, these structures occupy only a fraction of space. The majority of the universe's volume consists of voids, ranging from small pockets of low density to enormous supervoids like Boötes. In that sense, Boötes is not just an isolated oddity. It is a vivid illustration of the rule that space is mostly empty, punctuated by islands of matter and light. By putting Boötes in context with other voids, we begin to appreciate its unique combination of size, shape, and sparsity, as well as its role in the cosmic web. It is a rare example of a supervoid that stretches nearly uniformly across hundreds of millions of light years, a vast expanse almost entirely devoid of galaxies, and yet intricately connected to the surrounding filaments and clusters. Its extremity provides both a challenge and an opportunity for astronomers, allowing us to study the dynamics of the universe in regions where matter is almost absent and to understand the large-scale processes that shape the cosmos. With this context established, the next natural question arises: why is the Boötes void so surprising? Understanding its scale and emptiness sets the stage, but it also highlights why its discovery initially puzzled scientists, challenging existing theories of how structure forms in the universe and prompting deeper questions about cosmic evolution.
The Boötes void is not only remarkable for its size and emptiness, but also for the sheer challenge it presents to our understanding of cosmic structure formation. When astronomers first discovered it in 1981, they were astonished. While voids were theoretically predicted and smaller ones had been observed, the Boötes void represented an extreme outlier, a vast, spherical, and nearly empty region far larger than any void previously identified. Its existence raised immediate questions. How could such a vast emptiness form in a universe governed by gravity, dark matter, and the primordial density fluctuations of the early universe? And why had this void remained so sparsely populated, when models suggested that even underdense regions should still contain more galaxies? To appreciate why the Boötes void is so surprising, we must consider expectations based on standard cosmology. The prevailing models of the early universe, developed from observations of the cosmic microwave background and simulations of gravitational collapse, suggested that regions of slightly lower density would gradually empty out as surrounding denser regions drew in matter. Yet the scale of the Boötes void, 330 million light-years across, is extraordinary, far beyond the typical 30 to 100 million light-year range expected for large voids. While smaller voids are common and fit neatly within models of hierarchical structure formation,
Boötes appear to be an exceptionally rare and extreme case, prompting astronomers to reconsider the assumptions underlying their simulations. Another reason for the surprise lies in the void's relative isolation and smoothness. Many voids are irregular, shaped by the surrounding filaments and clusters in ways that produce jagged, elongated, or interconnected forms. The Boötes Void, by contrast, is remarkably spherical and internally uniform, with only about 60 galaxies scattered throughout its immense volume. Such sparsity is not merely a quantitative oddity, it is qualitatively different from the smaller, less extreme voids predicted by simulations. The combination of large scale, low galaxy density, and spherical symmetry seemed almost improbable given what astronomers knew about how the universe evolves. The implications of Boötes' extremity extend to our understanding of galaxy formation itself. In a void this large, gravitational interactions between galaxies are almost non-existent. Galaxies in the void evolve in isolation, untouched by mergers, tidal interactions, or the environmental pressures that shape galaxies in denser clusters. The discovery of such a region forced astronomers to question whether the models that accurately describe galaxy formation in clusters and filaments could also explain evolution in extreme underdense regions. It became clear that understanding Boötes required accounting for the full range of cosmic environments, from the densest knots of the cosmic web to the loneliest voids. The Boötes Void also challenged assumptions about the homogeneity of the universe on large scales. The cosmological principle, a foundational idea in cosmology, posits that the universe is roughly homogeneous and isotropic when viewed on sufficiently large scales. While voids do exist within this framework, a region as large and empty as Boötes seemed, at first glance, to stretch this principle to its limits. If a single void could span 330 million light-years, could there be other regions of similar scale or even greater? Were our maps of the universe complete? Or were there undiscovered features even more extreme? These questions prompted a reassessment of both observational surveys and theoretical models. Early speculation about the Boötes Void also included more exotic possibilities. Some astronomers considered whether it could be the result of a rare primordial fluctuation, or even influenced by unknown physical processes in the early universe. Others hypothesized that a large-scale phenomenon, such as a topological defect in space-time or an unusual distribution of dark energy, might explain its emptiness. While subsequent research has largely confirmed that Boötes is a natural consequence of density variations amplified by gravity, its extremity initially seemed to defy conventional understanding and stimulated significant debate in the astrophysics community.
The Boötes Void's discovery highlighted a profound truth. Even in a universe governed by predictable physical laws, extreme cases can reveal gaps in our understanding. It was a reminder that cosmology is not just about confirming expectations, but also about encountering the unexpected, testing the boundaries of what theories can explain. The void's size, shape, and sparsity forced astronomers to refine their models of structure formation, galaxy evolution, and the role of dark matter and dark energy in shaping the cosmic web. Moreover, Boötes serves as a tangible demonstration that absence can be as revealing as presence. While galaxies, clusters, and superclusters tell us about the accumulation of matter and the influence of gravity, voids like Boötes provide insight into what happens where matter is scarce. By studying such extreme regions, scientists can understand the dynamics of underdense environments, the impact of isolation on galactic evolution, and even the behavior of cosmic expansion in areas dominated by emptiness. Ultimately, the Boötes Void is surprising because it combines scale, isolation, and uniformity in a way that is statistically extraordinary. Its discovery forced astronomers to acknowledge that the universe is not just a web of matter, but also a tapestry of vast emptiness, where the extremes challenge our assumptions and expand the boundaries of scientific inquiry. In this sense, the void is both a puzzle and a beacon,
a place where the universe's structure is stretched to its limits and where our understanding of cosmic evolution is continually tested. Having examined why the Boötes Void is so surprising and how it challenges conventional models of cosmic evolution, the next step is to address common misconceptions about it. To clarify that, despite its dramatic emptiness, it is not a black hole, a wormhole, or a manifestation of some exotic anomaly, but rather a natural feature of the cosmic web. Despite its striking emptiness and enormous size, the Boötes Void is often surrounded by myths and misconceptions that exaggerate its nature. Its sheer scale and near-total lack of galaxies have led some to imagine it as a cosmic anomaly, a mysterious region with properties unlike the rest of the universe. Popular speculation has even compared it to a black hole, a wormhole, or a strange concentration of dark energy, but these ideas are inaccurate. The Boötes Void is neither a gravitational singularity nor a passage to another part of space-time. It is a natural feature of the universe's large-scale structure, arising from the same physical processes that shape the rest of the cosmic web. A common misconception is that the void functions like a black hole on a colossal scale. This analogy seems tempting, because black holes are regions where matter and light are absent in the sense that nothing can escape their gravitational pull. However, the comparison falls apart under scrutiny. The Boötes Void is not gravitationally dense, quite the opposite. It's a region of extremely low mass density, where gravity from the surrounding filaments and clusters actually pulls matter away rather than trapping it. There is no event horizon, no extreme curvature of space-time, and no mechanism by which light or matter is being swallowed. Instead, the void is essentially empty because very little matter ever accumulated there during the universe's formation. Another misconception frames the Boötes Void as a wormhole or portal to another dimension. Science fiction often portrays enormous gaps in space as tunnels connecting distant parts of the universe, but the Boötes Void has no such properties. There is no shortcut through space-time, no exotic physics allowing instantaneous travel, and no anomalous effects on surrounding galaxies that would suggest it is more than an underdense region. Observations of galaxy distribution, gravitational influence, and large-scale cosmic mapping all show that the Boötes Void behaves just like any other void, following the predictable laws of cosmology. Its vast emptiness is extreme, but not unnatural or inexplicable. Some also speculate that the void might be a concentration of dark energy, a place where the mysterious force accelerating the universe's expansion is somehow amplified. While dark energy does play a role in the growth of voids, its effects are not concentrated in Boötes in any unusual way. Dark energy acts uniformly across space, influencing the expansion rate everywhere. The Boötes Void is empty not because it contains excess dark energy, but because it started with slightly less matter in the early universe. And as gravity drew matter into surrounding filaments, it became increasingly underdense. Its emptiness is a natural consequence of cosmic evolution, not a sign of exotic forces. At its core, the Boötes Void is simply a region of space where galaxies are extraordinarily sparse. The processes that shaped it, gravitational attraction, expansion of the universe, and the amplification of initial density fluctuations, are the same processes that formed galaxies, clusters, and filaments everywhere else. What makes the void remarkable is scale. It is larger and emptier than almost any other void known, making it visually and conceptually striking. But in terms of physics, it is entirely ordinary, an extreme but predictable manifestation of the universe's structure. The idea of nothingness in the Boötes Void is also sometimes misunderstood. The void is not an absolute vacuum. It contains dark matter, intergalactic gas, and the faint background radiation that permeates the cosmos. These components, though invisible to the naked eye, play critical roles in the universe's evolution. Dark matter, in particular, exerts gravitational influence even in regions with few galaxies, subtly shaping the motion of matter at the void's edges. The void's interior is therefore not empty in an absolute sense. It is just extremely underdense, with visible galaxies scattered at vast distances. Another point of clarification concerns the shape and structure of the Boötes Void. Some might imagine it as a perfectly hollow bubble with a hard edge, as if someone carved out a spherical cavity. In reality, voids are not sharply defined. Their boundaries are gradual, marked by the increase in galaxy density as one moves toward surrounding filaments and clusters. The Boötes Void is roughly spherical, but this symmetry is an emergent feature of the gravitational evolution of matter, not an indication of any artificial or exotic process. By clearing up these misconceptions, it becomes evident that the Boötes Void is not a mysterious cosmic anomaly, but a natural extreme feature of the large-scale universe. Its vast emptiness is the result of ordinary processes: gravity, cosmic expansion, and the uneven distribution of matter in the early universe, amplified to an extraordinary scale. It reminds us that the universe is not uniformly filled with galaxies and stars. Instead, it is a tapestry of dense regions interwoven with enormous voids, each a testament to the dynamism of cosmic evolution. Understanding that the Boötes Void is a natural product of cosmology allows us to appreciate it without invoking exotic physics. It is a place where the universe simply did not deposit much matter, creating one of the most isolated and extreme regions we know. Its emptiness is profound, but its origin is fully consistent with known physics. This clarity sets the stage for exploring how astronomers know the void exists and how they can map such an enormous, nearly invisible structure using the distribution of galaxies. Astronomers do not observe voids directly in the same way they see stars or galaxies. Voids are defined by absence rather than presence. The Boötes Void, for example, does not emit light, shine brightly in radio waves, or reveal itself in X-ray surveys. Its existence is inferred through careful mapping of the distribution of galaxies. By plotting the positions of thousands and eventually millions of galaxies across the sky, scientists can visualize where matter is concentrated and, more importantly, where it is conspicuously absent. The void emerges as a vast, nearly empty region amid the dense filaments and clusters that form the cosmic web. The process begins with redshift surveys, which measure how light from distant galaxies is stretched due to the expansion of the universe. This stretching, known as redshift, allows astronomers to calculate each galaxy's distance from Earth, effectively giving them a three-dimensional map of the universe. When astronomers plotted these positions in the early 1980s, Robert Kirshner and his team noticed an enormous gap in the direction of the constellation Boötes, a region hundreds of millions of light-years across where very few galaxies appeared. It wasn't an optical illusion or a result of observational error. Subsequent surveys confirmed that the void was real. The Boötes Void is thus an example of detection by negative space. Instead of focusing on what exists, they identified it through what does not exist. By analyzing galaxy density in different regions of the sky, they could pinpoint areas where the density drops far below the cosmic average. In the case of Boötes, the average number of galaxies per unit volume is roughly 10 times lower than in surrounding regions, a deficit so extreme that it stands out unmistakably against the cosmic web. Modern surveys have further refined our understanding of voids. Projects like the Sloan Digital Sky Survey, SDSS, and the 2D Galaxy Redshift Survey have mapped millions of galaxies across large volumes of space, allowing astronomers to detect voids with unprecedented precision. These surveys use automated algorithms to identify underdense regions, measuring the distribution of galaxies in 3 dimensions and quantifying the emptiness of a given area. The Boötes Void consistently appears as one of the largest and most isolated regions in these catalogs, confirming its status as a supervoid.
Void detection also involves statistical analysis. Astronomers compare the observed number of galaxies in a region with the expected number based on the universe's average density. In the Boötes Void, the discrepancy is stark. While a volume of space that large should contain thousands of galaxies if matter were distributed evenly, only about 60 galaxies are found. This statistical contrast is so extreme that the void cannot be attributed to chance. It is a genuine, physical feature of the cosmic landscape. Mapping voids also benefits from multi-wavelength observations. While the galaxies themselves may be faint in visible light, radio and infrared observations can reveal additional galaxies that are otherwise hidden by dust or faintness. Even accounting for these, the Boötes Void remains extraordinarily empty. Its detection does not rely on exotic signals or direct imaging of the void itself. Instead, it is a testament to the power of indirect observation, the ability to infer vast structures from the pattern of what is present and, just as importantly, what is absent. Interestingly, the Boötes Void illustrates a key principle in astronomy. Absence can be as informative as presence. In a universe dominated by matter, the regions where matter fails to appear tell us as much about cosmic evolution as the clusters and superclusters do. By studying voids, astronomers can test models of how galaxies and clusters form, how dark matter is distributed, and how cosmic expansion affects underdense regions. The Boötes Void, because of its scale and extreme emptiness, provides a particularly valuable laboratory for these studies. The void's edges are also revealing. By examining the galaxies that form the boundary of Boötes, astronomers gain insight into the interaction between voids and filaments. Gravity causes matter to flow from low-density regions toward denser filaments and clusters, meaning that the edges of voids are often regions of enhanced galaxy formation. These boundary galaxies act as markers, delineating the void's extent and helping scientists define its shape. In this way, the Boötes Void is mapped not as a solid object, but as a volume defined by the sparse distribution of matter within and the surrounding density outside. Through these methods, redshift surveys, statistical analysis, and multi-wavelength observations, the Boötes Void has been confirmed repeatedly as a real, physical structure. It is not hypothetical, not an artifact of incomplete data, and not a mere projection on the sky. Its existence is inferred from the absence of galaxies on a scale so enormous that it dwarfs most other features in the universe. In essence, astronomers see the void not because of what is there, but because of the profound emptiness where something could exist but doesn't. By understanding how the Boötes Void is detected, we can also begin to imagine what it would be like to occupy this vast emptiness. To consider the perspective of floating inside the void, surrounded by near total darkness and separated from any other galaxy by tens of millions of light years, is to grasp the cosmic scale of solitude in a way that ordinary experience cannot convey. Floating in the middle of the Boötes Void would be an experience unlike anything imaginable on Earth or even in familiar parts of our galaxy. Unlike the night sky we see from our planet, filled with countless stars, the Milky Way's band stretching across the heavens, and the occasional glimpse of neighboring galaxies like Andromeda, the view from inside Boötes would be dominated by emptiness. In all directions, there would be a profound darkness, punctuated only by the faint glow of a handful of distant galaxies, themselves tens of millions of light years away. This is true cosmic isolation, a silence and darkness on a scale that is almost impossible to comprehend. To put this in perspective, the nearest galaxy to our Milky Way, Andromeda, is about 2.5 million light-years away. In the Boötes Void, galaxies are separated by distances more than 10 times that, meaning that even the brightest galaxies would appear as tiny, almost imperceptible points of light. From the center of the void, an observer would likely see less than 100 galaxies across the entire sky, compared to the hundreds of billions visible in a typical patch of the universe. The Milky Way and all its familiar neighbors would be completely isolated, surrounded by a vast, empty cosmic desert. The night sky inside Boötes would lack the familiar tapestry of stars. Stellar light, which in denser regions of the universe illuminates the darkness, would be almost entirely absent.
The few galaxies present would appear as tiny smudges of light, dim and distant, and the void itself would dominate the perception of space. For an observer accustomed to light-filled skies, this would be eerily quiet and profoundly alien, a reminder of how relative human experience is when compared to the universe on its largest scales. The void would feel like a vast, spherical cavern, with the edges defined not by walls or surfaces, but by the rare locations where galaxies begin to appear again in the surrounding filaments and clusters.
Even with advanced telescopes, observing from within Boötes would present challenges. Ordinary starlight from individual galaxies would be faint, and the distances between them so extreme that gravitational interactions would be negligible. There would be no tidal forces, no collisions, no mergers to light up the void with bursts of star formation or galactic fireworks. The few galaxies that do exist would evolve largely in isolation, maintaining their faint glows for billions of years without the influence of nearby neighbors. In essence, the void is frozen in quiet solitude, an almost timeless environment compared to the bustling activity of clusters and filaments. The emptiness would also amplify the scale of cosmic structures in a perceptual sense. In denser regions, the sky is filled with galaxies and clusters, giving a sense of structure and proximity. Inside Boötes, by contrast, distances become incomprehensible. Tens of millions of light years separate the observer from the nearest galaxy. Light from these galaxies, traveling at 186,000 miles per second, would take tens of millions of years to reach the observer, meaning that one is effectively looking far into the past. The galaxy seen would be ancient and isolated snapshots of a universe unfolding slowly in near solitude. From a psychological perspective, the view would be both humbling and unsettling. Human beings are accustomed to filling space with objects, stars, or landmarks. To gaze across the Boötes void is to confront true emptiness, a scale of isolation that challenges the imagination. The observer would realize that the vast majority of the universe, even on the scale of the observable cosmos, is not filled with luminous matter but dominated by emptiness. The experience is not merely an absence of stars, it is a confrontation with the loneliness of the cosmos, a place where the normal rules of density and proximity are stretched to the extreme. Yet, even in this apparent nothingness, there is structure. Subtle traces of dark matter and intergalactic gas permeate the void, forming a gravitational framework that shapes the few galaxies that exist. This underlying scaffolding is invisible to the eye, but crucial in defining the void's boundaries. In a sense, the void is not entirely silent or featureless. Its emptiness itself tells a story, showing where matter failed to accumulate and highlighting the dynamics of the surrounding cosmic web. Imagining the view from inside Boötes also emphasizes the relativity of cosmic scales. Even the largest galaxy clusters, like our local supercluster, would seem insignificant from this vantage point. The void dwarfs all familiar structures, stretching across hundreds of millions of light years, and within it, even a galaxy like the Milky Way becomes a tiny, lonely outpost. This perspective transforms our understanding of the universe. What we perceive as vast and populated is, on the largest scales, merely a small patch of light in a dominantly empty cosmos. Finally, the perspective from within Boötes is a reminder that emptiness itself is meaningful. The void is not a mistake, a glitch, or a cosmic anomaly. It is an integral part of the universe's architecture. From inside, one would feel the magnitude of cosmic isolation, but also the elegance of large-scale structure, how matter clumps into filaments and clusters while leaving vast regions like Boötes empty. The view is stark, chilling, and awe-inspiring all at once, capturing the essence of the universe's extremes and forcing the observer to reckon with the scale, solitude, and profound beauty of cosmic emptiness. Understanding this view sets the stage for appreciating why the Boötes void matters to science, how studying it informs our knowledge of the universe, and why astronomers consider these regions not as lifeless voids, but as laboratories for understanding cosmic evolution, dark matter, and dark energy. Voids like the Boötes Void are far more than curiosities. They are critical laboratories for modern cosmology, offering insights into the fundamental forces and components that govern the universe. While dense regions of the cosmos filled with clusters and galaxies reveal how matter accumulates under gravity, voids reveal the opposite, how emptiness evolves under the same physical laws. By studying these under-dense regions, scientists gain a unique perspective on the behavior of matter, energy, and the expansion of space in conditions vastly different from those within filaments or clusters.
One of the primary areas where voids inform science is dark matter. Although invisible, dark matter dominates the mass budget of the universe and acts as the gravitational scaffolding around which galaxies and clusters form. In dense regions, the influence of dark matter is often intertwined with visible galaxies, making it challenging to disentangle the contributions of baryonic, ordinary matter from its dark counterpart. In voids, however, the paucity of galaxies simplifies the picture. The motion of the few galaxies within and at the edges of the void is largely governed by the surrounding dark matter distribution. By carefully analyzing these motions, cosmologists can map the density and distribution of dark matter in a way that is nearly impossible in crowded regions. The Boötes Void, with its extreme emptiness and well-defined boundaries, provides one of the clearest laboratories for this kind of analysis. Voids also offer critical clues about dark energy, the mysterious force driving the accelerated expansion of the universe. The rate at which voids expand over cosmic time is sensitive to the interplay between gravity, which pulls matter together, and dark energy, which pushes space apart. Because voids are already underdense, the influence of dark energy is more pronounced than in regions filled with matter. By measuring the growth of voids and comparing it to theoretical models, scientists can test different hypotheses about the nature of dark energy, its density, and its behavior over time. In essence, studying voids allows cosmologists to observe dark energy in action across some of the largest scales in the universe. Additionally, voids provide a natural testing ground for understanding the expansion of the universe itself. The universe is not a static backdrop, but a dynamic entity stretching and evolving over billions of years. In regions like the Boötes Void, where matter is scarce, the expansion is less impeded by gravitational attraction, allowing these areas to grow faster than surrounding dense regions. By mapping the size and growth rate of voids, astronomers can refine models of cosmic expansion, helping to reconcile observations with theoretical predictions from the lambda-cold dark matter model, the standard framework for cosmology. Voids also play a role in understanding galaxy formation in extreme environments. The few galaxies inside the Boötes Void evolve in isolation, largely free from mergers, tidal interactions, or the influences of nearby clusters. Studying these galaxies provides insight into how star formation, gas dynamics, and chemical evolution proceed in environments drastically different from dense regions. By comparing void galaxies to those in filaments or clusters, astronomers can isolate the effects of environment on galaxy evolution, providing a clearer picture of the underlying physical processes. Another scientific application of voids lies in testing theories of the early universe. The initial fluctuations in density that eventually produced voids, filaments, and clusters are encoded in the cosmic microwave background. Observing extreme voids like Boötes allows cosmologists to connect the present-day universe to its primordial conditions, checking whether models of inflation and early structure formation are consistent with the existence of such massive underdense regions. In this way, voids act as a bridge between the distant past and the observable present, offering a window into the universe's earliest moments. Furthermore, voids can eliminate the distribution and behavior of intragalactic gas. Even in underdense regions, diffuse gas permeates space. By studying how light from background quasars is absorbed as it passes through these voids, astronomers can map the density, temperature, and composition of intragalactic gas in environments far removed from the crowded cosmic web. This contributes to our understanding of how baryonic matter is distributed throughout the universe, and how it interacts with dark matter and dark energy on large scales. The Boötes Void in particular is a benchmark for all these studies because of its extremity. Its enormous size, near total lack of galaxies, and relative isolation amplify the physical effects under study. Observations of Boötes allow cosmologists to stress test theoretical models, checking whether simulations of the universe naturally produce voids of this scale, and examining whether any adjustments to our understanding of cosmic physics are necessary. In doing so, it serves as a kind of cosmic laboratory, a place where the universe itself tests our assumptions about structure formation, dark matter, dark energy, and expansion.
Studying voids also has a broader philosophical implication. It reminds us that the universe is dominated by emptiness rather than matter. While galaxies, stars, and planets capture our attention, they occupy only a small fraction of space. The majority of the universe's volume consists of voids, with Boötes representing one of the most extreme examples. By focusing on what is missing, scientists gain insight into the universe's large-scale architecture, including how the interplay between presence and absence shapes the cosmic web. In summary, voids like Boötes are far from irrelevant gaps in space. They are essential tools for understanding fundamental cosmology, providing unique insights into dark matter, dark energy, cosmic expansion, and galaxy formation. Their emptiness, rather than being a limitation, is precisely what makes them so scientifically valuable. By studying these vast regions where matter is scarce, astronomers can isolate and examine the forces and processes that shape the universe in ways impossible to achieve in denser environments. The Boötes Void, with its extraordinary scale and sparseness, stands as a monument to the universe's extremes and a key to unlocking the secrets of cosmic evolution. The scale of emptiness in the Boötes Void is almost beyond human comprehension. To fully grasp it, consider the Milky Way, a galaxy that itself spans approximately 100,000 light-years across. Now imagine placing our entire galaxy at the very center of the Boötes Void. The nearest neighboring galaxies wouldn't be a few million light-years away, as in our local cosmic neighborhood, but tens of millions of light-years distant. The vast, dark expanse surrounding the Milky Way in this hypothetical scenario would dwarf every familiar astronomical distance we experience or can intuitively imagine. The universe in this context transforms from a network of interconnected galaxies into a stark, lonely ocean of space. To appreciate the magnitude, consider that the Boötes Void stretches about 330 million light-years across. That means it is more than 3,000 times the diameter of the Milky Way. Millions of galaxies like our own could theoretically fit within this enormous volume, yet only about 60 actually exist there. This disparity reinforces the staggering emptiness of the void. The human mind struggles to picture such distances, and even the most sophisticated simulations and visualizations cannot fully convey the true isolation within its bounds. This is emptiness on a scale where cosmic time, light travel, and gravitational influence all operate under conditions drastically different from anything familiar. The Boötes Void occupies a noticeable fraction of the observable universe's structure. The observable universe is vast, with a radius of roughly 46 billion light-years. Yet the Boötes Void, at 330 million light-years in diameter, commands attention as one of the largest known regions of underdensity. When mapping the cosmic web, the void appears as a gargantuan bubble, a massive cavity among the intricate filaments and clusters that trace the universe's matter. Its presence reminds us that emptiness dominates volume even when light-filled regions capture our imaginations. While filaments, superclusters, and galaxy walls form the bright threads of the cosmic web, the spaces between them, the voids, occupy the majority of the universe's volume. The sense of scale is further intensified when considering the relative isolation of the galaxies within the void. The sparse 60 or so galaxies scattered throughout Boötes are separated by tens of millions of light-years, meaning that even gravitational interactions, mergers, or tidal effects are extremely rare. Unlike the crowded environments of clusters where galaxies collide, merge, and influence each other's evolution, the galaxies inside Boötes live in near total solitude. If we were to observe one galaxy from the center of the void, we would see the nearest companions only as faint distant specks, their light taking tens of millions of years to reach us.
In this sense, the Boötes Void is not just empty, it is profoundly isolating, amplifying the scale of cosmic distances to the point that normal intuitions about proximity break down. This emptiness also emphasizes the role of the cosmic web in shaping matter distribution. The Boötes Void exists not in isolation, but as part of a larger network of filaments and voids. Surrounding it are massive superclusters, galaxy walls, and intricate filaments where matter has concentrated over billions of years. Gravity has pulled material away from the underdense region of Boötes, feeding the growth of these dense structures. The result is a stark contrast, an enormous, near-empty cavity bordered by regions teeming with galaxies. This juxtaposition makes Boötes a striking example of how cosmic structures emerge from initial density fluctuations, highlighting both abundance and absence on unimaginably large scales. Even in relative terms, the void's emptiness is dramatic. In other voids, a few dozen or a few hundred galaxies might exist in a comparable volume, but Boötes is extreme in both size and sparsity. Its boundaries are clearly defined by the surrounding filaments, which accentuate the sense of emptiness within. If one could traverse from one edge of the void to the other at the speed of light, it would take over 300 million years, more than twice the age of the dinosaurs, to cross from one side to the other. This scale transforms emptiness into a tangible feature, a measurable and almost physical entity in the cosmos, rather than a mere absence. Visualizing the void also highlights the relativity of cosmic density. In the Milky Way, nearby galaxies like Andromeda, the Magellanic Clouds, and the Virgo cluster give the illusion that galaxies are plentiful. Yet Boötes demonstrates that the universe is mostly not crowded. The galaxies and clusters are exceptions, the luminous pearls in an otherwise dark expanse. Its sheer size forces us to confront the fact that the majority of the universe's volume is empty space, a principle that fundamentally shapes the dynamics of cosmic expansion, dark matter distribution, and the evolution of structure. In summary, the Boötes Void reinforces both the physical and psychological scale of cosmic emptiness. It is a cavernous space where galaxies are few and far between, where distances stretch across hundreds of millions of light years, and where our intuitive sense of proximity is rendered meaningless. If the Milky Way were placed at its center, all other galaxies would appear as faint, distant dots in a vast black expanse, emphasizing how emptiness dominates the cosmos. The void is not merely a curiosity, but a tangible measure of the universe's immense scale, an extreme manifestation of the large-scale structure that shapes both presence and absence in the cosmos. The Boötes Void challenges our understanding not just of space, but of what nothing actually means in a cosmic sense. When we think of a void, the instinctive image is of an absolute emptiness, a region devoid of matter, light, and energy. But in the universe, absolute emptiness does not exist. Even the Boötes Void, one of the most extreme underdense regions ever discovered, contains subtle traces of matter and energy that hint at the underlying structure and activity of the cosmos. What we perceive as emptiness is more accurately a region of extremely low density, where the usual markers of cosmic structure, galaxies, clusters, and filaments, are sparse or absent, but where the universe still hums with faint, omnipresent energy. One component that exists even in the deepest voids is dark matter, the mysterious and invisible substance that outweighs ordinary matter by a factor of roughly 5 to 1. Dark matter does not emit, absorb, or reflect light, making it effectively invisible to telescopes. However, it exerts gravitational influence, and even within the Boötes Void, dark matter forms a diffuse scaffolding that shapes the motion of the few galaxies scattered throughout the void and subtly affects the surrounding cosmic web. Far from being a perfect vacuum, the void contains a skeleton of gravitational potential that persists across hundreds of millions of light years. In this way, dark matter is a reminder that nothing is never truly nothing. It is simply a region where ordinary matter is sparse. Another persistent feature is the cosmic microwave background, CMB, the afterglow of the Big Bang. This radiation fills the entire universe, permeating both dense clusters and empty voids alike. Even in the Boötes Void, the CMB provides a faint, nearly uniform glow at microwave wavelengths, a subtle echo of the universe's infancy. Although it is invisible to the naked eye, this background radiation is present everywhere, an unbroken thread of energy connecting the emptiest regions to the most crowded galactic clusters. The presence of the CMB emphasizes that voids are not truly empty, but rather relatively empty, containing energy that predates the formation of galaxies, stars, and even the cosmic web itself. Intergalactic gas is another constituent of voids. Though extremely tenuous, traces of hydrogen and helium, relics of the Big Bang, drift throughout the Boötes Void. This gas is so thin that it is almost impossible to detect, but its existence can be inferred through subtle absorption lines in the spectra of background quasars and galaxies. These ghostly wisps of matter illustrate that even the emptiest regions are filled with diffuse material, albeit at densities millions of times lower than in a typical galactic environment. This underlines the idea that nothing in space is relative. The void is far less dense than the surrounding universe, but it is not an absolute vacuum. Even the most dramatic voids are subject to quantum fluctuations and faint gravitational waves, contributing to the subtle activity within them. The universe is never perfectly still. Energy is always present in some form, whether as the motion of particles, residual radiation, or the faint gravitational tug of dark matter. In this sense, the Boötes Void hums quietly with the faintest echoes of cosmic energy, a reminder that absolute emptiness is an idealization rather than a physical reality. The concept of nothingness in the Boötes Void also carries philosophical implications. To an observer placed in the center of the void, the night sky would appear almost completely black, with only a handful of distant galaxies punctuating the darkness. This visual emptiness might feel like true nothingness, but in reality, the void is filled with invisible structure, energy, and matter on scales that defy human perception. It demonstrates that emptiness is a relative concept, defined not by the absence of all phenomena, but by the absence of familiar luminous matter. The universe, even in its loneliest regions, is never truly silent or inert. It contains subtle traces of the forces and components that govern all of cosmic evolution. The existence of matter and energy in voids has practical scientific consequences. Even at such low densities, the diffuse dark matter and intergalactic gas within Boötes affect the motion of the few galaxies present, as well as the growth of surrounding filaments and clusters. The void itself expands slightly faster than denser regions, partly because of dark energy, and these differences in expansion rates are measurable. By studying voids, scientists can probe the influence of dark matter and dark energy in environments that are nearly free from the complicating effects of galaxy interactions, making them valuable laboratories for cosmology. Moreover, the quote-unquote nothingness of the Boötes Void allows researchers to test the limits of structure formation. The extreme underdensity demonstrates that the early universe contained regions where matter was unusually scarce, and the fact that these regions persisted over billions of years confirms the influence of gravitational evolution, cosmic expansion, and the distribution of dark matter. In essence, the Boötes Void is a physical manifestation of the universe's initial conditions, a space where the faint whispers of the Big Bang are still detectable amidst the absence of ordinary matter.
Ultimately, exploring the nature of nothingness in the Boötes Void expands our understanding of the universe. It shows that even regions that appear utterly empty are filled with subtle structure, energy, and potential. The emptiness is profound, yet it is also a canvas on which the universe's history is painted, revealing the processes that govern matter, energy, and cosmic expansion. The void's existence reminds us that in the cosmos, absence is as meaningful as presence. Both are integral to the story of everything, from the earliest moments of the Big Bang to the ongoing evolution of the cosmic web. Contemplating the Boötes Void invites a psychological as well as scientific reflection. Even for professional astronomers, understanding its scale is a challenge. Human intuition evolved to navigate landscapes measured in meters, kilometers, and perhaps a few hundred kilometers at most. When faced with distances spanning hundreds of millions of light years, the mind struggles to grasp the enormity. The Boötes Void is not just physically vast, it is conceptually staggering. It exists as a nearly empty cavity within the cosmic web, reminding us that the universe is mostly empty space, and that the stars, galaxies, and clusters that capture our attention are relatively rare islands in a sea of darkness. From a psychological perspective, thinking about the Boötes Void can evoke a profound sense of cosmic humility. Imagine realizing that everything familiar, our solar system, the Milky Way, even the nearby Andromeda Galaxy, occupies an infinitesimal fraction of space compared to the emptiness surrounding Boötes. The human mind tends to anthropomorphize or overestimate the presence of matter in the universe. Our daily experience is full of density and proximity. Boötes, however, challenges this assumption. It reveals a cosmos where emptiness dominates, and where light, matter, and energy are concentrated in only tiny filaments and clusters. Psychologically, this confrontation with vast emptiness can be both awe-inspiring and unsettling, forcing us to rethink our place in the cosmos. The void also prompts reflection on isolation on an unimaginable scale. Unlike isolation experienced on Earth, which can be remedied or measured in minutes or hours, the Boötes Void offers isolation on a scale that transcends human comprehension. If one were hypothetically situated at its center, the nearest galaxy would be tens of millions of light years away. Even light, the fastest thing in the universe, would take tens of millions of years to travel between neighbors. The sheer loneliness of this environment is difficult to imagine, yet it is a real physical phenomenon. It is a reminder that most of the universe exists in silence and darkness, far removed from the bustling neighborhoods of galaxies that are the focus of human observation. Yet, this psychological encounter with voids is not purely of despair or emptiness. There is a sense of wonder and awe in realizing that the universe is capable of producing such extremes. The Boötes Void is a testament to the beauty of cosmic structure, a place where absence itself is remarkable. Its scale and isolation make it an object of fascination, compelling humans to stretch their imagination and confront realities far beyond the limits of everyday perception. In this way, voids like Boötes are not just astronomical objects, they are mental exercises, forcing us to expand our understanding of space, time, and existence. Moreover, contemplating Boötes highlights the contrast between presence and absence in the universe. When we look at the night sky from Earth, we are dazzled by the stars, yet those bright points occupy a tiny fraction of space. The vast darkness surrounding them is the true fabric of the cosmos. The Boötes Void exemplifies this principle in extremis. It is a region where absence is overwhelming and presence is minimal. Psychologically, it reshapes our intuition about the universe, teaching that most of reality is not composed of what we can see, but of what is absent, vast regions of underdensity stretching for hundreds of millions of light years.
The void also invites reflection on human cognitive limits. Our brains are adapted to perceive patterns and distances on human scales, not on the scale of hundreds of millions of light years. When we attempt to imagine Boötes, we are forced to grapple with concepts that cannot be directly experienced. Distances so vast that light travel itself becomes a meaningful measure. Isolation so extreme that galaxy interactions are non-existent. And emptiness so profound that ordinary notions of density fail. This confrontation with the incomprehensible evokes a mix of humility, curiosity, and awe, underscoring the mental challenge of comprehending the universe in its totality. Finally, the Boötes Void reminds us that cosmic significance is not tied to abundance. While humans are naturally drawn to bright stars, dense clusters, and spectacular galaxies, the most representative feature of the universe may be emptiness. The vast voids, including Boötes, occupy the majority of cosmic volume, shaping the expansion of space, the distribution of dark matter, and the evolution of the filaments and clusters that contain most of the luminous matter. By confronting such emptiness, we gain a deeper appreciation for the scale and structure of the universe, understanding that both what exists and what is absent contribute to the cosmic story.
In essence, the psychological wonder of the Boötes Void lies in its combination of scale, isolation, and emptiness. It forces humans to grapple with dimensions and concepts far beyond our everyday experience. It challenges intuition, inspires awe, and provides a profound reminder of the universe's true nature. Most of it is darkness, silence, and solitude, punctuated by rare pockets of light and matter. Recognizing this reshapes our understanding of the cosmos and our place within it, highlighting both the majesty and the mystery of the universe. In recent decades, our understanding of cosmic voids, including the Boötes Void, has advanced dramatically thanks to large-scale galaxy surveys and sophisticated mapping techniques. Projects like the Sloan Digital Sky Survey (SDSS) and the 2DF Galaxy Redshift Survey have revolutionized cosmology by cataloging millions of galaxies across vast stretches of the universe. These surveys allow astronomers to chart not only the locations of galaxies, but also the voids that separate them, providing an increasingly detailed picture of the cosmic web. The Boötes Void, once identified as a singular extreme, is now studied in the context of countless voids, helping scientists understand how these enormous underdense regions form, evolve, and interact with the surrounding universe. The SDSS in particular has been instrumental in mapping the three-dimensional distribution of galaxies to unprecedented precision. By measuring the redshift of millions of galaxies, the survey allows astronomers to determine distances and construct volumetric maps of the universe. In these maps, the Boötes Void emerges as a vast, roughly spherical underdensity, while other voids of varying sizes and shapes populate the cosmic web. Modern analysis reveals that voids are not merely empty bubbles, but complex regions shaped by the gravitational influence of surrounding filaments and superclusters. This level of detail enables scientists to study subtle properties of voids, such as their internal galaxy content, dark matter distribution, and expansion dynamics.
Beyond mapping, recent research has focused on understanding the physical properties of galaxies within voids. Galaxies that reside in underdense environments like Boötes are rare, and their isolation offers unique insights into galaxy evolution. Without frequent interactions or mergers, these galaxies evolve more slowly, and often retain primordial characteristics that can inform models of star formation, chemical enrichment, and galactic morphology. Observing such galaxies with advanced telescopes, including those operating in radio, infrared, and ultraviolet wavelengths, provides clues about how environment influences galactic life cycles. In essence, the Boötes Void acts as a natural laboratory for studying galaxies in near-pristine conditions. Void research has also expanded into understanding cosmic expansion and dark energy. Modern surveys allow astronomers to measure the growth of voids over cosmic time, comparing their current sizes with predictions from theoretical models. Since underdense regions expand faster than denser regions due to weaker gravitational pull, the rate at which voids like Boötes grow is sensitive to the universe's dark energy content. By tracking void evolution, researchers can test and refine models of cosmic acceleration, helping to constrain the properties of dark energy, and improve our understanding of the universe's large-scale dynamics. Furthermore, surveys such as SDSS have enabled the study of void statistics. Scientists examine the distribution, shapes, and sizes of voids across billions of light-years to test cosmological models. The Boötes Void, as one of the largest known voids, provides a benchmark against which simulations can be compared. Observations confirm that while voids are common, extremely large ones like Boötes are rare, offering critical constraints on structure formation theories. These statistical studies help verify that the lambda-cold dark matter model accurately predicts the observed void distribution, or conversely, indicate where refinements may be necessary. In addition to galaxy surveys, modern research has leveraged gravitational lensing and cosmic microwave background measurements to probe voids more deeply. Gravitational lensing allows astronomers to infer the presence of dark matter in and around voids by observing the subtle distortions of background galaxy light. Even in a region as empty as Boötes, these distortions provide evidence of the underlying dark matter framework. Meanwhile, studies of the CMB, particularly phenomena like the integrated Sachs-Wolf effect, reveal how photons traveling through underdense regions experience subtle shifts due to cosmic expansion, offering another way to study the physics of voids indirectly.
Technological advancements in telescopes and data processing have also allowed for void mapping at higher redshifts, extending our view of these structures further back in cosmic history. Surveys like the Dark Energy Survey, DES, and upcoming missions such as Euclid and the Vera C. Rubin Observatory aim to provide even more detailed void catalogs, tracking the evolution of underdense regions across billions of years. This will improve our understanding of how voids grow, merge, and interact with the cosmic web, offering new insights into the history and fate of the universe. Modern research also emphasizes multi-scale studies, analyzing voids of various sizes to understand the hierarchical nature of cosmic emptiness. The Boötes Void represents an extreme, but smaller voids, mini-voids and subvoids, reveal the layered structure of underdensities, showing how emptiness is not uniform but organized within the large-scale fabric of space. Understanding these relationships helps scientists refine simulations, making them increasingly accurate in reproducing the observed universe.
In short, contemporary research has transformed voids from curious anomalies into essential cosmological tools. The Boötes Void is no longer merely a distant curiosity, it is a key feature within a broader context of cosmic structure. Surveys like SDSS, DES, and future missions continue to study it in ever greater detail, providing critical data on galaxy evolution, dark matter, dark energy, and cosmic expansion. Each observation of Boötes and other voids adds to a growing understanding of the universe's true shape, revealing that emptiness is not mere absence, but a fundamental and measurable component of the cosmos. The Boötes Void stands as one of the most remarkable structures in the observable universe, distinguished not only by its scale, but also by what it reveals about cosmic evolution. Its enormous size immediately sets it apart. Stretching roughly 330 million light-years across, it dwarfs entire superclusters and could theoretically contain millions of galaxies the size of the Milky Way, yet it houses only about 60. This extreme contrast between expected and actual galactic density underscores the Boötes' uniqueness and compels astronomers to study it closely as an outlier in the otherwise intricate cosmic web. Its sheer dimensions alone make it a landmark in the universe, a feature that dominates the landscape of space on scales we can scarcely imagine. Equally striking is the sparsity of matter within Boötes. Unlike the dense filaments and clusters that dominate the universe's luminous regions, Boötes is a near-total vacuum of galaxies. The few galaxies it contains are widely separated, evolving in near isolation and largely unaffected by the gravitational interactions that shape galaxies in clusters or filaments. This isolation provides an unparalleled laboratory for studying galaxies in extreme environments, revealing how star formation, gas dynamics, and chemical evolution unfold when external influences are minimal. The sparse contents of Boötes, therefore, are not merely an absence, but a rich source of scientific information, offering insight into both the extremes of galaxy formation and the influence of cosmic underdensity. Perhaps most importantly, the Boötes Void serves as a window into the organization of the universe. It is a striking example of the large-scale structure of space, where galaxies cluster into filaments and walls, leaving vast underdense regions like Boötes in between. The void's existence validates models of structure formation, in which small initial fluctuations in the early universe were amplified over billions of years, causing matter to accumulate in dense regions and leaving emptier regions behind. By studying Boötes, scientists gain a clear picture of the universe's skeleton, observing directly how gravitational dynamics, dark matter, and cosmic expansion sculpt the cosmic web. It is a tangible demonstration that emptiness is not a flaw or anomaly, but a fundamental and measurable component of the cosmos. Boötes is also special because it challenges and refines our understanding of cosmic evolution. Its enormous size and extreme underdensity raise questions about how structure forms on the largest scales, and whether current models fully capture the complexity of the universe. The fact that a void this vast exists implies that early density fluctuations must have been finely tuned, providing constraints on cosmological theories and simulations. It forces scientists to reconcile the existence of such an enormous empty region with the otherwise relatively uniform distribution of matter predicted by the standard cosmological model. In this way, Boötes is both a test and a guide, showing where models succeed and where they must be refined.
Moreover, the Boötes Void reminds us that emptiness itself carries meaning. Far from being a simple absence, its vast emptiness highlights the contrast between regions of abundance and scarcity,
showing how matter organizes itself across cosmic scales. Every filament, cluster, and galaxy is defined in part by the spaces between, and Boötes exemplifies this principle at an extreme. Studying it helps cosmologists understand how gravity, dark matter, dark energy, and cosmic expansion interact to create the large-scale patterns we observe today. Its significance lies not just in what is missing, but in how that missing matter shapes and informs the surrounding universe. Boötes is also special from a perceptual and philosophical standpoint. It embodies the vastness and isolation of the universe in a way that few other objects can. To imagine standing at its center, surrounded by near total darkness, and separated from other galaxies by tens of millions of light years, is to confront the scale and solitude of cosmic space. This experience, though hypothetical, deepens our appreciation for the universe's extremes, emphasizing that the cosmos is dominated not by luminous matter, but by the expansive emptiness in which it is embedded. In summary, what makes the Boötes Void truly special is a combination of enormous scale, extraordinary sparseness, and its critical role in understanding cosmic structure. It is not simply an empty region of space. It is a profound clue to the processes that shape the universe, a natural laboratory for studying galaxies, dark matter and dark energy, and cosmic expansion and the visible manifestation of the universe's large-scale architecture. Its emptiness is informative, its isolation is instructive, and its sheer size commands both awe and scientific attention. Boötes reminds us that the story of the universe is as much about absence as it is about presence, that in the cosmic web, both voids and filaments are essential to the grand tapestry of everything. Boötes ultimately leaves us with a profound reflection on the nature of the universe and our place within it. At first glance, emptiness might seem unremarkable, even unimportant. Yet the very existence of Boötes, a space hundreds of millions of light years across, almost entirely devoid of galaxies, forces us to reconsider the meaning of nothingness. It demonstrates that absence can be just as significant as presence. In the grand cosmic architecture, the spaces between galaxies, the voids that dominate volume, are not void of meaning. They are essential components that shape the evolution and distribution of matter across the universe. Thinking about the Boötes Void also emphasizes the duality of existence and absence in the cosmos. Filaments, clusters, and superclusters of galaxies are the visible threads of the cosmic web, the luminous signs of matter gathering under gravity over billions of years. The voids, by contrast, are the negative spaces that give the structure definition and context. Without regions like Boötes, the universe would be a homogeneous expanse, lacking the intricate contrast that defines its large-scale structure. In this way, emptiness is not merely a lack, it is a canvas upon which cosmic evolution is written, a stage upon which the dynamics of galaxies, dark matter, and dark energy play out. From a human perspective, the void also evokes a sense of awe and humility. It is difficult to overstate the scale. Distances measured in tens or hundreds of millions of light years. Galaxies scattered sparsely across a space so vast that light itself takes millions of years to traverse. The Boötes Void challenges our intuition and expands our perception, reminding us that the universe operates on scales and in patterns far beyond human experience. To comprehend even a fraction of this emptiness is to confront the limits of imagination and the magnitude of the cosmos.
Yet this vast emptiness is not meaningless. Each sparse galaxy, each faint hint of dark matter, every whisper of intergalactic gas within Boötes contributes to a deeper understanding of cosmic history and structure formation. The void's existence confirms predictions of gravitational evolution, illustrates the influence of dark energy, and provides a natural laboratory for testing theories of galaxy formation. In other words, Boötes is a testament to how absence can inform knowledge, how nothingness can be as instructive as the presence of matter. The Boötes Void also inspires a philosophical reflection on our place in the universe. Humans are naturally drawn to stars, galaxies, and clusters, the luminous and tangible, yet the cosmos is overwhelmingly empty. Most of the universe's volume is taken up by spaces like Boötes, silent and dark, stretching across unimaginable distances. Recognizing this transforms our understanding of the universe.
It is not merely a collection of stars and galaxies, but a vast architecture of matter and emptiness interwoven, where both light and shadow define the grand design. In contemplating Boötes, we are reminded that even nothing can inspire wonder. The void is a cosmic paradox, an emptiness that is rich with meaning, a lack that reveals the laws of physics, a silence that tells a story. It exemplifies the principle that the universe's most profound insights often come from places we might overlook, from the spaces that are largely devoid of matter but full of significance. Studying Boötes teaches us that the universe's extremes, its densest clusters and its most desolate voids, together narrate the full history of cosmic evolution. Ultimately, the Boötes Void shows that the universe is a story of contrasts, presence and absence, density and emptiness, light and darkness. These opposing forces define the cosmic web and the dynamics of the universe. By appreciating both the luminous filaments and the silent voids, we gain a holistic understanding of the cosmos. The void reminds us that everything we see, and everything we do not see, has meaning. Even nothingness is instructive. Even emptiness is awe-inspiring. And even isolation on the largest scales contributes to the grand narrative of existence. In closing, the Boötes Void invites us to reflect not only on the scale and structure of the universe, but also on our perspective as observers. It challenges us to recognize the significance of absence, to marvel at the extremes of cosmic architecture, and to appreciate the subtle interplay between light and darkness that shapes everything we know. The void is a silent teacher, a vast expanse that humbles the mind while expanding it, and a reminder that in the cosmos, both presence and absence tell the story of everything, from the birth of galaxies to the unfathomable depths of emptiness itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.